can get started. So welcome everyone to the afternoon tutorial on sports models in R. So to get started, I first just wanted to introduce myself. So my name is Stephanie. I'm a data scientist at Tennis Australia in our Game Insight group, which is sort of a research and development group for tennis performance analysis. And I'm also a fellow at Victoria University in Melbourne. I also created a blog on tennis stats. If you have interest in tennis, from a numbers point of view, you can look at the On the Tee site for some stories that we do there. And I usually tweet out about those stories on my Twitter account at Stats on the Tee. Now, the materials for today, you should have already received an email from me about the materials, and I've put the address there as well. So I created a repo that has all of the slides that we'll be going over in the R Markdown files that created those slides so that you can follow along. I think that's going to be the best way, since we have a lot of material in a short amount of time this afternoon to try to get through. It's probably going to be best to have each of those Markdown files open as we go along so that you can actually run the code. So we probably all are here in part because we really enjoy using R. And one of the things that's great about R is that it's very interactive and you learn by doing. And I hope that we can do that today, and the easiest way is going to be using those materials. So if you haven't already downloaded that, I would suggest going to that site and then going to download that repo. And I've organized the repo into separate folders for each of the parts that we'll be going over. So those parts are starting first, we're going to talk about web scraping, and I'll show some specific examples of the kinds of sports data that you can scrape and methods available in R to do that scraping depending on the types of data that we're accessing. And then the rest of the tutorial is going to focus on several types of common models used with problems in sport. And there's going to be 4 different types of models that we'll go over. So it should cover quite a good range of common models used in sport. So to get started, if you are commonly doing analysis of sports data, you'll find that you often will have to gather data from the web. Now, there are a lot of resources out there where you can potentially already find some sports data from packages in R, but there often are some limitations that you're going to run into, particularly if you want the most up-to-date data that's available. So we're usually in the situation where we have to scrape. There are some basic categories of scraping that we can do, and I just want to run over each of those, and so you have an understanding of the different types of data that you can find on the web and the different methods that you'll use for each of those types. So one is simply importing data from a file. So sometimes you'll come across data that's already been provided as in a downloadable file. So that's one way that you can come across data. More commonly, you're going to have to find that data through actual scraping of the underlying source code or data for dynamically generated pages. So when we're dealing with data that we have to scrape, that can either be done in static HTML, or if the data is dynamically generated, we can find ways of actually importing that if we can get at the data backend, or we can automate browsing to effectively turn that dynamic data into static data. Okay, so we're going to go over each of those in this section on scraping. So first, in the situation of importing, this is really kind of the best scenario. If you can actually find a file that contains the data of interest, then it makes things very easy because you can basically have a single command, almost like you would a file that's locally stored on your system, you can just then read that in using common import commands like read table, read CSV. So, for example, the baseball reference site, which has data on results in baseball, it has a number of those historical stats in CSV files. So that would be an example of a type of importable file. So other types, basically anything that could be read in by the read table command would be examples of file types that you could just do an import statement if they were in that format on the web. And so in that case, you're just giving then the URL address where that file is located, just as you would a file that was stored locally on your machine. So as an example of how this would work, and we can go to the markdown file here under the scraping RMD if you want to run this example yourself. So here we're looking at a file that's stored at the tennisdata.co.uk. So this is a site that has tennis results and betting odds for the match winner for tennis. So here you see the name of the tournament is the Oz Open. So this is for the Australian Open 2017. So if I run this, then we'll see that I effectively get a data frame back, as I would expect from the import read CSV command, and it has information about the matches that were played at this particular tennis tournament. Okay, so it's as easy as that when you're able to find a site that has these data already available in a file. Now, looking at that example, what do you think you would have to do if you wanted US Open data from that same site and results in a similar way? What would change? Delete the A. So you're guessing that, okay, well, they probably all follow this pattern where it's year, tournament name, and if this is the name for the Australian Open, then maybe the US Open is just the US Open. And you would be right. And an easy way to check that is to actually open up a browser to see if that location exists and that file is there with the format that you expect. So one thing when you're getting into web scraping is if you're going to be doing this kind of activity repeatedly, and you found a site that, say, is updating after certain events or sporting competition happen, then you do want to start to look for these kinds of patterns in the URLs, and we'll see more examples of this as we go on. Okay. Now the importing, it's nice, but actually finding files that have all the data you would want about your sport of interest is pretty rare. More often, you're going to have to actually go under the hood and look at the source page of interest for the site that you're getting your data from in order to get all of the data that you might want. So let's talk a bit more about, now this is really where web scraping comes in. So let's talk a bit more about the kinds of data that you can come across and how you would extract those different types. In doing this, you're going to need some other tools outside of R to really understand which R scraping methods are most appropriate for the data that you have. And for that, I would suggest finding the developer tools for your browser of interest. I think Chrome is particularly good at the kind of developer tools that they provide, and those are the examples that I'm going to be presenting, but I think any browser will have a similar set. You may just have to put in like an add-in or plug-in to make those available to you. So essentially, these are going to be things that assist you in looking at the underlying source code and elements of the page and this will help you to identify the type of data that you're working with. So here's an example. This is looking at a basketball reference page, and in Chrome, I would go under View, and there would be a developer selection that would allow me to go to a number of options. The view source will just go directly to the HTML code underlying that page. Developer tools will open up even more information about the elements and allow you to do a bit more, have a bit more control over selecting different sections of the page and identifying what parts of the HTML code they correspond to. So just as an example, if you want to go to the basketballreference.com site, we can open that up. So I'm going to go to Chrome, and so we can see how this would usually work. Okay, so I'll just expand that a bit. Okay, so if I go to View, and I go to View Source, now you'll see what opens up is mostly not very human readable. There's a lot of stuff that's probably different scripting commands at the top, and then eventually we get to sections that are in HTML. So this is typically what you're going to come across. You can also see that a shortcut, rather than going through View, you can actually just type view-source and then a colon and then the URL, and it will have the same result. Okay, so let's suppose that we were interested in the NBA standings data, and we wanted to try to find out. So you see here, this NBA standings, it has tables that have data about the wins and loss records of various teams by their division. So that might be, if I were interested in doing some analysis of basketball box scores, match game results, then this might be data that I would want to import. So looking at the view source, how would we go about trying to find out what elements that data is contained in? So when we're starting to scrape, what we're looking for when we're assessing the HTML page, the source code, we're looking for information in the HTML structure that will help us identify those data of interest. So here, if we're interested in the NBA standings, I want to find what elements that data is contained in, and if there's anything like an ID or class element that would help me uniquely identify those data. So one thing you could do is to take some of the text you see on the page and just do a simple search to try to get to that element. So if I say NBA standings, I see it takes me to a division section in the source code. And if I scroll down, I start to see information here about conference standings, and this E suggests that it corresponds to the Eastern Division. If I scroll further, now I start to see that actual data that's in that table. So I know now that I'm in the right section of the source page for those particular standings, and that's the starting point for figuring out how am I going to actually export or import that data into R. It also points out a very basic difference in the way that data is generated on these sites, and that is the difference between static and dynamically generated data. And these are really two distinctions that are key in making when you're designing your scraping method. Okay. The basic difference is that static data is data that you can see when you look in the source code. It is in the HTML. If it isn't there, that means it's dynamically generated. Sometimes you can get a sense what's dynamically generated just based on how you interact with the page itself. So if there's a lot of like clicking that you have to do to see any of those data, that might be a clue to you. If you see like windows popping out and then it's showing you the result, that is the kind of situation where you would expect that to be dynamic data. But really you want to go into the view source, the source, to confirm what type it is. So let's get a little practice with this. Here's a site from the tennis abstract, which has different stats on tennis. So if we go to this site, what I'd like you to do is to use view source, whichever browser you're using, to look at the HTML source and determine whether you think this data is static or dynamic. And once you have an idea, share it with the group if anyone has an idea. So it seems to not be loading. Are you guys having trouble loading it? Yeah, I don't know. It seems to be hanging right now. Is that true? Let's see for the WTA as well. Is it the Wi-Fi connection? Okay. Let's try. So if we do the data camp, let's see if that's more reliable. I think it was, free trial. Are people having the same issue on the data camp Wi-Fi? Uh-huh. Okay, let's see. So this is supposed to have a bigger bandwidth. I'm not sure if that's going to help. Let's see. Yeah, it might have something to do with that page. Okay, well, let's go. So what we should see when the page is active is this source. And so essentially the page has information about ELO ratings of players, which is a way of rating the player's strength at any particular time. And we can see that there's a table in the HTML code that has those rating information. So we would see the same data in the table in the source code, and that would tell us that it is statically generated. Okay, let's see if we can do this example, if the whole site's not down. Yeah? It really just depends on the web designer because, they'll decide how often they're going to be updating. If they're wanting to update very frequently, then I would expect that they would probably go with a more dynamic option because that's just going to be more efficient. It also can depend on the amount of data that they're presenting, but it really is just dependent on their design preferences. Okay. Well, let's see if we can go to another example. So here's another site that I've been using quite a lot recently. It's SofaScore, which is a site that does live scoring for a number of sports. So we can go, for example, to the football, since that's quite timely at the moment with the World Cup going on. And let's do a view source. Let's say that we were interested in some of the data here, which is showing results for anything that's happening in the, well, this is all for today, or recently completed matches. So this might be data that we would like to collect if we were doing some analysis of soccer results. So if I go to view source, I would want to find those standings. So for example, I see information about Brazil. We can try to search for Brazil to see, and I'm not finding any of that text that I see here on the page. So what does that suggest? It's dynamic data, because I'm not seeing those values actually in the HTML content, okay? So that's the basic process of making this distinction. And we'll see why that's important when we see the different ways that we would get these data. So for static data types, there are different ways you could go about doing this. Some are more or less efficient. So the most basic would be doing a read line. So once you have that URL for data that exists within the HTML, you could do a read lines, and then what that would return you is just a vector that goes line by line in that code. But then you're stuck with having to parse all of that that's there and all of the HTML tags around the values that might be the only thing that you're really interested in, and then you've got to get that into a tidy data set. So you'd like to avoid having to go there if you can. Again, that might depend, though, on the design structure. So if the web designer has put things into a nice table, for example, then that's much easier to deal with, and there are tools like rvest that we'll see here that you can actually almost directly import those HTML data into a data frame structure in R. So it helps to avoid some of the parsing and things. So rvest, it's a suite of tools for scraping web data, and it follows the kind of syntax of the tidyverse packages. So you can also have the kind of piping commands that you may be used to with dplyr, for example. And it's written by Hadley, so it has a lot of the syntax that you're familiar with in the tidyverse. So those are all reasons why it's particularly easy to start using. So let's see an example. Here we saw previously that the basketball reference data was static. We could see those division standings in the page. So that's data that we can try to scrape directly using the rvest package. So the first step that we're doing here is just reading in that data. So I create the location of the page that has the data I'm interested in, and then to just read that in, I just use the read_html command from the rvest. Okay, so let's see what that gives us. So it's this section of the markdown. Okay, so you'll see that we can look at the class type return. So it's contained in sort of an XML object structure. So it's not yet a data frame, because basically it contains all of the content of the page. We still need to give it more information about the specific section of interest to isolate that part. So how do we do that? This is where it's important to look at the elements around that data of interest. So we were looking to find where the standings information was. And if you find either a tag element, so the CSS here that you see the argument in the HTML nodes, that refers to the style elements. So you could give one of those. For example, it could be an A if you're interested in reference links. Here we're using table because we found that the NBA box scores were contained within a table element. So what this will do, I give the HTML nodes to the web page that we had already collected, and I'm giving the table node. So it's going to look for every table structure in that document and return just the content within that. And then I apply the HTML table to actually just process and pull out the values contained within the table. And what will be returned is a list. That's the length of the number of tables that were in that document. And then each element will be a data frame structure or list structure of the data that it includes. So we'll see when I do this, I look at the length of the list. So it found 7 different tables in that NBA page. And we can look at one of those, for example, just to get an idea of what kind of information was returned. Okay, so we're seeing different score results. But the thing is notice that we did not have to do any parsing, and we're already, getting some useful information. It's just a matter of isolating the particular table or tables of interest. So how can we make this more specific? Let's say that I really only want the Eastern Division standings. As an alternative to table, which can be maybe overly broad sometimes if it's a fairly complex page where there are multiple instances of that particular CSS element, then I could be more specific by using an XPath. So these are the two main options that we have when specifying the nodes with rvest, is either some kind of CSS element or an XPath. The XPath, it's a whole type of language with XML, and you'll notice that it has sort of some wildcards and special characters. So it's almost like a regular expression type of thing, like you'd have to read up to know exactly how to do what you're trying to do. But here's an example. If I wanted to isolate the division standings, I could use the ID element. Now, where did I get that from? So let's go back to this view source. And if I look for the division standings, you'll see that the table of interest, it starts in this section of the code, and you'll see that there's an ID element here that's equal to the division standings. So that's what's going to be isolated when I specify this XPath. Okay, so I'm indicating the element of interest and what its value is, and the XPath will isolate that. And then I request the table that's contained within that division with that ID. So this table. And that should give me just that specific section of the document. So if we run that, you should get this data frame returned, and you'll see that it contains the win-losses that we see on the page for the Eastern Conference. Okay. So this is essentially the basic step that you'll find when you're working with static data and using rvest, is essentially identifying the elements that uniquely identify the data of interest, and then it's generally a set of HTML table or HTML text to then extract that. And then there may be a little bit more parsing that you'll have to do depending on exactly how you want that data formatted. But it goes quite a long way when you have sort of a nice static structure like that. Another thing I should point out is that, again, kind of recognizing the patterns in the way these are structured. Normally, a designer that has any experience is going to use pattern sort of elements in their design. So if I wanted the Western division standings as well as the Eastern, then I know that it's probably just a matter of changing this one letter to W to get that data. And you can then imagine having a function that could run through all of the division standings where it's just changing one part of the string, but all of the rest of your scraping code looks the same. Okay, so I had a practice example here with the ratings, but since it looks like we're having trouble accessing that, I'll just leave that one. You could also use other parts of the basketball or any of the reference, sportsreference.com sites to practice with the rvest scraping. One shorthand, so one thing that you can do to specify particular tables is look at their class type, and sometimes you might find that a table has a specific class. So in this case, this particular ELO ratings page, it had a class called table sorter was its value. So the shorthand in rvest to indicate a table with a particular class is just table dot and then that class name. And that's another way to try to uniquely identify that particular table of elements so that you're not getting a list of many tables that you might not be interested in. So that's kind of the crash course on static data. Okay, so before we go on to dynamic data, were there any questions on the rvest static stuff? It's pretty straightforward. So most of the examples I've encountered can be handled with this kind of sequence of steps, and most of the work is simply in looking at inspecting the page and just figuring out what are the elements of interest. Okay, so dynamic data. This is the more complicated situation, but it is one that we can handle. So even though the dynamic data is a little bit more challenging to get at, we can still do it, and we have two main ways of getting at it. So one, I kind of think of as sleuthing, and this has to do with being able to find sort of the back end to the data that is generated on that site. It's not always possible to do, depending on how that site is designed, but it's a good first thing to look, because usually if you can get at that back end, it's much easier than having the alternative, which is automating the browsing to try to make your dynamic problem a static one. Okay, but we can do both, and I'll show you how that would work. So first, on this sleuthing, what am I talking about here? So the dynamic data, it has to come from somewhere, and often designers will put the data, so somewhere it will probably be on the server, and then it will be created in, let's say, JSON or XML files to be quickly exported with JavaScript, typically. In those cases, sometimes we can find the source of those JSON and XML files and actually import them directly. So it's just a matter of finding out where they're located, being able to access where they're at, and if we can do that, then this essentially becomes an import step. So to find out if you can do this, I think the easiest way is using the developer tools, and there's a section of XHR, which is the XML HTTP request, and that basically tells you about where user requests of data are happening and where you can find out where that request is coming from. And that will generally be, if you are getting JSON or XML generated files, you can sometimes find where those are located, and that gives you the URL that you need to import the same data. And you can generally see in the response field where that's happening. So let's go back to that SofaScore site, and we'll open up the developer tools so I can show you what I mean. Okay, so I'm still looking at the... So I'll go to SofaScore, and we want the football section. Okay, so I'm in the football section, and I'm going to open up the developer tools. So you'll see like a box section open up here. Let me see if I can expand this. Okay, so you'll see here's that XHR element that I was referring to. Sometimes you'll need to refresh to actually start to register actions. But here I'm going to click on some things, and you'll see the XHR updating. Okay. Okay, if I expand this a bit, now you'll notice below there are some elements coming up, and I'm going to click on some of these to get information about what's going on there. So the request URL is the thing that we're interested in, because that's potentially where some data could be stored. And if I want to see exactly what's associated with that particular URL, I can look under the response. And now I look here, and I'm starting to see, okay, there's some information here. I'm seeing team names, countries, goal information. And then I can look back on the site to try to understand, where exactly that information is coming from. But the main point is, once I see this, I know that there's at least some of the data on this site that I can effectively import as JSON files. And then it's just a matter of finding out what that address is. Okay, so as an example, we can look at the standings. And let's say we are interested in exporting or importing some of these standings data. Into R. Because this data is as JSON files, I would use the JSON-Lite package to read these into R. So all I have to do, it's much like that importing that we saw. I get my URL address, and then because it's as JSON and not CSV or text, and I want to bring that in as a data frame, I can use the from JSON function from the JSON-Lite package, and that will try to put that into a nice structure. So let me show you the full address since it was cut off a bit in that page. So here's the full address, and then the result, it's actually a list because there's quite a number of nodes in that JSON structure. But as an example of some of the data that's returned from that particular site, I see it looks like it's one of the group results of the World Cup. But that was really simple. It was just, the only challenge was really finding that URL address, and that was just a matter of using these developer tools. Okay, so then once you've been able to do this, then it kind of reduces your problem to finding the patterns for all the different types of data you want, and then doing any parsing that you're going to need. Because if you have this list structure, it might mean that you're having to pull multiple elements from that list to get the final data frame that you may be interested in. But that's much, much easier than what you're going to encounter with the automated browsing scraping that we'll see in the following slides. So I already mentioned a bit about looking for patterns in the URL. We saw that the data that was returned here, it seemed to have to do with one particular group. Okay, so we had, this was our URL, and this was what return. Let's suppose I was interested in a different group. Looking at that structure, what do we think might be what we would have to modify to get different group data? Yeah, so it looks like there's a couple sections here, if we look at that original URL, that seem to be maybe some kind of ID. And if you experiment a bit on the site, you'll find that this element here appears to be a kind of group ID for the World Cup results. And then by clicking elements on the site and seeing how the XHR information updates, you could find that, for example, the 3959 is an ID for a different group in the tournament. So that's an example where a combination of using the inspection and then some trial and error, you can start to see what the patterns are in the URLs. And then this would be a thing if you're trying to create, let's say, a batch process to collect all of the group results, that it really just becomes a matter of a substitution and replace within that URL string, and all of the other steps would stay the same because the design of because the scripts underlying that site generation are always going to apply in the same way. So you're essentially almost deconstructing the way that it's built up to make it easier to collect these data sort of in a more automated way rather than having to go to a site and like copy and paste into Excel or something like that, which would be heinous if you wanted to do this for a lot of data. Okay, so that's sleuthing. It's really about getting used to those developer tools and expecting that XHR element. Unfortunately, sometimes you're not going to be able to do this because either the data won't be formatted in that way, it won't be designed in that way, or you'll be blocked from accessing those elements. But you can still get at that data, just as a little more steps involved. Effectively, what we have to do is to automate the browsing process so that we see the data that we're interested in. And the way to do that, I think most easily currently, is using Selenium, which is software that exists outside of R, and it's used for automated web browsing. And there's a package rSelenium which allows us to access those tools within R. Now, Selenium requires other sort of external software like Java in order to function. So I've suggested utilizing Docker so that you can ensure that you're using the adequate requirements to get Selenium running without having to worry about all of the installation and kind of incompatibility issues that can come up. Now, that being said, I know that some people have run into issues on Windows in installing Docker, so I think the Docker toolbox is more stable on Windows. So unfortunately, it's a bit easier to get ready using Docker with Linux or Unix-based systems. And, but I think it's still possible to do. If you haven't been able to set that up before today's tutorial, it's okay. You can follow along, and then if it's something that you think you're really going to want to use in your work or research, we can chat during the break or after today's sessions about what you might need to do to get set up with it. But for now, you can follow along to just see what the purpose is. So the point of Docker is really just to have kind of a virtual image of the software that you need to run Selenium. It's not something that is required. I just think it generally will make things easier. Once you have Selenium set up, the basic workflow is to create a web driver, which is basically the browser that you're going to be using to browse to the pages of interest, then you're going to have to find the elements. And we've already seen examples of how to do that. You'll just now need to specify that within the functions of R Selenium. So the syntax will look a little bit different, but it's still the same process of looking for elements in the HTML that identify the data of interest. You'll then provide some functions to extract the content once you found those elements, and then the parsing. And in this case, unfortunately, the parsing will be more involved because you're going to get the data in a bit more of an unstructured format than the nice tables that we saw with rvest or with reading in the JSON files. Okay, so if you're working with Docker, you'll look for the Selenium Docker images, and there will be different options depending on the type of browser that you want to use. So it could be Chrome, it could be Safari. It's your choice. In this example, I'll be using the Firefox browser. So once you have Docker running, and you can generally see up here, this little whale icon indicates that I have Docker currently running on my system. And I can just open up a terminal or the command prompt if you're on Windows. Let me see if I can expand this a bit so you can see. The first thing I'm going to do is first check if I have any jobs currently running. So I can use the ps command to see if there are any jobs running. And this indicates that there is not anything. So I can start a new Docker image at my port of choice. So I'm going to choose the 4445, which is generally going to be a port that won't be used. Okay, and then it's as simple as this. And then I'll see sort of an ID assigned, and that will be an indication to me that Docker is now running. Okay, so that's just getting me set up. Now here's an actual example of a site with dynamic generated data. So this is from FlashScore, which is another live scoring site like SofaScore. Unfortunately, on this site, I've not been able to find a way to just import that data. The data backend eludes me, so maybe you guys can find it. I haven't been able to, so I've been using automated browsing on this site. So this is an example of a match summary for a tennis match. This is actually the Australian Open men's final. This is data, as a tennis statistician, this is data that I'm interested in being able to scrape. So I can use the R Selenium to do this. So I just need to get that URL information. And if I look at the source, and I'm trying to identify the elements that may give me this info. Now, it's a little more challenging in the case of this dynamic data because you won't see the data. So sometimes you won't know exactly where you need to look to get that. So sometimes you'll have to go, it'll be some trial and error, and hopefully the designer will use some clues based on the naming around the elements. So here you see the class sports tennis, and the ID detail might suggest that it's maybe more of the stats info. Okay, so this is the initial process that you would have with scraping with R Selenium. So we would load R Selenium. We've got Docker on the port 4445 in the background. I have my URL now, so I would initiate this driver for Selenium using Firefox with this remote driver command. And then I'm just going to assign that to an object that I'm going to call remdr for the driver. I'll then open that to just initialize that browser. And then I'll execute the navigate command to go to that particular URL. Now, because we're using Selenium, you won't actually see anything happening if you were running this locally and you didn't set your driver to silent and you weren't using like a Phantom JS browser, then you would actually see your browser open and you would see the particular page you navigated to when you executed the navigate command. So let's see if we can get this running. If I go to this section of the Markdown document, we should be all set up. Okay, and we'll see some information about the connection, and then once it connects, it will give me some return information about the status of that connection. And then it's still navigating to that particular URL. So I'll let that go in the background. Okay, once we've gone to that URL, and I know information about the likely element of interest, I would use the find elements to actually extract that particular section of the page. So to indicate which kind of tag or node in the rvest language that I want to use, I would use the using argument. And then the next argument would be a value that takes. So here I'm saying I want to go to where the ID is equal to detail, that part of the web page, and I'll assign that to this object web elem. And then I run through the web elem, which will be a list, and each time I'm going to ask to get any text that's associated with that element of the web elem object. And so that will return any text, and like I said, it will be unstructured. And if I'm done at that point, whenever I'm finished with my navigation and extraction, I can close my driver by issuing the close command. So that should be your last step when you're doing the automated browsing. Okay, so it looks like one issue with the automated browsing is that it will generally be slower. It's less efficient than the other methods that we said. So that's one of the downsides, in addition to getting sort of unstructured text. But sometimes it's our only option. Okay, so let's see if we can get another example to run on our conference website. Okay, so this is another example of dynamic data. It's come from an NFL site. So I already have my driver open, so I would just try to navigate to a different site. And let's see if this one does better at connecting. So this is what the site looks like. We see it would contain results for different years, and you can see how the URL changes depending on what information you want. So you could go back to the different seasons by just changing the year in this URL. So this one, it seems to be going a bit slowly as well, which may have to do with the Wi-Fi connection here, or running directly in R might actually make a difference as well. So in this case, if I went to the view source on that site, in this case, there would be a class element that I could use to try to identify a particular standings of NFL team results. So all I would modify would be the using argument and then the value that it would take. But you'll notice that otherwise the steps look very similar. It's find the elements and then extract the text from that. And in this case, I see some of the results with the team names in the list that's returned. Okay, so unfortunately I couldn't show the exact examples for the Selenium results, but I hope that you still get an idea of how to identify the difference between the static and dynamic data, and that we can look for dynamic data that has a backend that we can access through tools like the developer tools that are available with current browsers. And if that's not possible, we can fall back on some of these automated browsing services, facilities in R, and they'll have some drawbacks associated with them, but it can still help make the scraping process more efficient than if you're trying to collect these data manually, particularly if you're going to be doing this multiple times repeatedly as these sites are updated, or if you're wanting to go back historically where that historic data may be available. And just in general, these tools apply to all kinds of data that you can find. It's not limited just to sports data, so I think this is a section that can be particularly broad, I guess, in its application. So anytime you're thinking of collecting data from the web, you should consider some of these tools to help in doing that, particularly if it's something that you think you'll do repeatedly, because you can see how these could easily be written and wrapped into functions. And I can point out a few, if you're interested in maybe seeing some more examples of these kind of tools, I can point out a few repositories that I have on GitHub that do this sort of thing. So one of them that I've been working on recently is for scraping data from the SofaScore site. Actually, this one I have under our gig site. So you'll see under the gig tennis, I have a SofaScore package, and it will have a number of examples of sort of functions for accessing and reading in. So there'll be a lot of examples with sort of parsing JSON files. And then for more kind of examples of automated functions, I have this gig web package. And this will give examples of scraping from sites like FlashScore. And there'll be a mix of rvest. So you can see there'll be a mix of examples of sort of string manipulation and actual fetching of data using the Selenium tools, since most of that data on FlashScore is dynamic. So a few resources if you're interested in doing more work like that. Most of my examples are in tennis, but I still think there's kind of broader applicability. Okay, so was there any questions on the web scraping before we get into our modeling section? Yes. Yes, I'm glad you brought that up. So if you are going to be doing like heavy extracting of data or doing it regularly, it would be good to look at the terms under that site to see if there are any limits in terms of, I mean, that data is public, so you should be able to access it, but as a courtesy to the administrators of that site, and if there are any particular terms in how that they want that data to be used or not used, you should be familiar with that if you're going to be heavily using any particular site. Yeah. So generally on their landing page, there will be a section that you can find terms of use, and if it's not clear, then I would contact the web administrator if you're concerned about the data uses. Yes? So I think in terms of what you see in the links, that you would be able to access kind of the metadata associated with the results, which would be true for any Google search page results. I think the difficulty there is that they come in these sort of page structures. So you would need some system of, being able to navigate through all those pages. So I think it would still require a mix of sort of static and dynamic data, since you won't know exactly how much content is, because that's going to depend on the nature of that particular query. But yeah, I think these similar tools would apply. I've worked on a package for exporting queries from PubMed. And so there's actually, if you do any research in health, you probably have used like the NCBI databases, and they have a set of utilities that allow you to specify queries in URL and to effectively automate the queries as you would enter them into a PubMed database or so on. And so something like that is quite easy to bring in, and that has a certain subset of citation information for journals that are covered by those databases. So that would be something that would be a bit more straightforward. Google Scholar is a bit, as you see, it comes out on the search results, it's a bit unstructured, but you would be able to get some information with these methods. Okay, so let's get started then. And now that we have methods to try to get at these data, what are some of the things that we might do with them as a sports statistician? So the first type of model that I wanted to go over is paired comparison models. And let's see, if we open up, so I'll now be going through the material in the paired comparison markdown document, if you want to open that up. Okay, so in sport, often it's about head-to-head competitions, either two teams competing against each other or two individuals. Many sports fall into this kind of structure. So we're usually interested in making some kind of comparison between teams or athletes. Often the comparison that we're most interested in is who's going to win. And those win outcomes give us some information about the relative abilities of competitors. So the abilities, it's not something that we actually can observe. We see results, but as like the World Cup shows us with so many draws that can happen, let's say in the round robin stage, we know that even a 0-0 score doesn't mean that those two teams are necessarily equal. So there's something about the underlying abilities that goes beyond just what the results from that competition tells us. And this is the thing that these paired comparison models are trying to help us get at and give us an actual way to quantify the abilities based on some outcomes that we can observe. So let's suppose we're in this framework where we have two competitors going against each other, and we want to know something about the relative abilities of those competitors. So I'll just refer to competitors A and B, and their abilities as delta A and delta B. what are properties, if these deltas represent ability, what would we expect the properties of them to be to favor one of those competitors over the other? So if I actually had values to these deltas, what might be something that would indicate to me whether I should favor A over B? Yeah, so if we, let's say, looked at results and we had some measure of strength that we could observe, which is here I'm saying the abilities is like the strength of the team or competitor. The better competitor, I would expect to have the greater ability. So one basic property is that we would expect the ability to increase with the strength of that opponent. So actually getting numbers and finding out about those relative differences in ability, one way that we can do that is with a particular kind of paired comparison model called the Bradley-Terry-Luce, or sometimes you'll just hear it referred to as a Bradley-Terry model. And this model, it encapsulates the idea that competition outcomes do give us important information about the underlying abilities of competitors. So if we have a model that relates those abilities to those outcomes, we can try to actually estimate those latent ability measures. The equation that you see here is the basic approach for doing this in the Bradley-Terry framework. So we see the probability of competitor A winning is expressed in this exponential form. And you'll notice that here, this model all comes down to the differences between those abilities. So if I know the difference, that's all I need to know to estimate the likelihood that one competitor is going to win over the other. So that's the basic strategy with these paired comparison models. Yes? Yep. Mm-hmm. Mm-hmm. Yeah. No, yeah, you're going way ahead. But that's a great point. So in the most basic form, it looks at abilities only as your ability to win. And so it's kind of encapsulating everything. But you're right, like in a team sport type of situation, you might expect that there's an offensive and a defensive ability, and a team isn't necessarily great at both or equal in both. But the combination of the two is going to contribute to their win outcomes against a particular opponent. So there are versions that can try to separate those two. But in the most simplest form, to introduce the basic idea, we'll just focus on, suppose we can assign a single ability to these competitors and how that would work. So as I said, the basic properties that come out of this model are that everything comes down to the differences in abilities in determining the likely outcomes of competition. It also tells us that if the abilities are equal, then we would expect a fair chance, okay? So if we have 0 here, then that's going to give us a 50-50 chance, which makes sense in that case if you have equal abilities. Another thing that we can see is that there's roughly an addition of 10% for every added difference in ability of 0.4 in this. So that's just one thing that you can say in this particular form. So another thing to keep in mind, because this all comes down to the differences, any single ability itself doesn't have much meaning. Its meaning only really matters in relation to the difference that it implies against other opponents. And here you could just plot this particular logistic form. Essentially, we have a logistic form for the Bradley-Terry model, and it gives you an idea of how win expectations vary as we vary the difference in competitor abilities. So how would we actually implement this particular model? Well, there's a package called the Bradley-Terry 2 that's available in R for doing the basic BTL models. It also allows you to incorporate covariates, which we'll see in our examples can be particularly useful. One of the authors of the package, Heather Turner, is actually here at the conference, so if you're interested in knowing more about this package, you can find her and chat about it. To get started with the Bradley-Terry modeling in the Bradley-Terry 2 package, the main function that you're going to work with is the BTM function. And this is its basic syntax. It has an outcome vector, and this will be the outcome with respect to competitor 1. And even though it's called player 1, player 2, this could equally be a team. So it's fine. It's just the general argument name. So outcomes will refer to player 1. And then player 1, player 2, those both have to be vectors that are factors, and they have to have an equal set of levels. So all of the same teams or player names are represented in each of those factors. And that's really all you need to get started. So now let's use some of the scraping that we saw previously to get some data that we can use the Bradley-Terry on. So here I'm going to take some soccer results, and this is going to be for the Premier League. And I'm going to just save that data as an object called data. So you can just find that code in the Markdown. And go ahead and have a look once you read it in, inspect just what the contents of that data include. So you can do something like view the data, or a struct argument, or just head to see the first few rows. So when you look at the data, you'll see a number of variables. The ones that we're most interested in relation to the basic form of the model are going to be the competitors, who is playing whom, and then the results. So for that, we're going to need to know the names of the teams in the league, when they competed against each other, and then what the goals were for each of those teams, so we can determine the winners and losers. So in this data set, that information is going to be in these 4 variables. We have the home team, away team, and then the goals for the home and away teams respectively. Okay, so to fit our first Bradley-Terry model, we want to get that data into the structure that we need for the BTM function. So as I said, we need the outcome, and then we need factor versions of the competitors, ensuring that they have the same number of levels. So the way that I've done that is just shown here. So our outcome is just going to be a win or loss. So we're going to attribute the outcome to the home team if the home team had the greater number of goals. And then the home team variable, we're just going to convert that into a factor and make sure that it has all of the levels that are represented among the unique instances of the home team and away team. And then once I've done that, I can just assign the away team factor to the same levels that the home team has. So here I'm using dplyr for these manipulations. And these are all just variable transformations, so we can just do that with the mutate statement. Okay, and then once I've done that, I can easily fit the first Bradley-Terry model by just then specifying those 3 variables and then the data set where those variables come from. So I'll go ahead and run that example. Okay, so now we have the fit object, which is going to have the results. Now, like most model methods in R, it's going to come with some standard methods like print, summary, and some plotting methods. So once you fit, go ahead and you can see examples of each of those. You can take fit and just hit return to see what the print method returns. You can do a summary of the fit object. And so you'll see that the results are quite similar to what you would get with a GLM, for example, other type of regression objects. So we'll notice that there's a set of coefficients, there's a team name, and then estimates associated with each of them, along with standard errors and significant values associated with each of these. So these estimates correspond to what measures of the Bradley-Terry model. Yeah, these are the information about the strength, the ability measures of interest, right? Because those are the only parameters that we've specified in the model. We don't have any covariates. We just have our outcomes and then our team matchups over all of the matches that they've played. Yep. So if we don't specify otherwise, the reference will be the reference that the factor forms. So by default, the factor will just do it alphabetically. So for the EPL, it will make Arsenal the reference. Yeah, it'll become the reference. So all of those estimates that you see are comparisons against Arsenal. If you wanted to modify that, you could simply specify the reference in your factorization of the teams. Yes, we're going to get to that. Yes, you're a football fan, I can tell. Okay, so for now, I just want to point out the abilities. You can look at them a bit more easily with this BT abilities function that the package provides. And so you would just apply that to the fit, and then what it will do is return ability measures for all of the teams along with a standard error. So now you'll see what your reference is. That'll be set to 0. So these are all on a log scale, which is fine. I mean, you can also convert them into the exponential scale if you'd like, if you want to make your reference set to 1. But with this structure, then, you might imagine that with the Bradley-Terry, you're most interested in the relative abilities and the uncertainty around them. So this function would give you an easy way to be able to start to plot them or summarize them and get a better understanding about the interpretation of the results. So I've just given an example of putting that into a data frame structure that I can then more easily summarize into a plot like this, for example. So you can see in the R Markdown, I'm just using some ggplot commands to plot that the ability information. So if we look at this, now we're looking at the 2017-2018 season. So what would be the interpretation, some of the things that we can take away when we look at this summary for our most basic version of this model? Yeah, it looks like in terms of just our point estimate, that Man City stands out as the strongest team. And we have a number of teams that their point estimates are higher. So there are 5 teams that appear to perform higher than Arsenal. And then a larger majority that were estimated to be lower in strength. Okay, so what are some of the shortcomings? One was already pointed out. Did anyone catch that comment? What's a shortcoming with the way that we've set up this model? Now this, you need a little bit of context about football. Yeah, so one thing is we've ignored a general idea about a home field advantage. So there's nothing that we've incorporated to deal with a home field advantage. And also in football, in the EPL, you can have draws. And we've essentially assigned a loss for every draw. We've assigned a loss to the home team. So that's potentially a problem if it turns out that ties are a significant proportion of outcomes. So let's look at how we might deal with this. So with the home advantage, this is something we can actually deal with by introducing a covariate into the model, which is one of the nice features about the Bradley-Terry models in this package. So to do that, it's a little bit different than you might imagine. It's not simply a matter of putting in a variable into our modeling equation. We have to actually change the structure of the home and away team information. So effectively what we do is create a data frame for each of the teams, in this case home and away, and then we would indicate the covariate variable that corresponds to that particular team. So in this case, the home team's always at home by definition, so we assign a 1 for the home covariate, and then a 0 under the away. And then the way that our modeling command would change is we still have the same outcome, but now we're going to give, for our player 1 and player 2 variables, we're going to give those data frames, and then we have to specify some information to let the modeling function know where it's getting its team information and where it's getting the covariate information. So the way that we structure it, if you saw, we have the team variable and then the at-home variable. So our formula will just be using the formula syntax that we're familiar with in other standard models in R. We'll use the tilde, and then we'll just give the variable names for the team and the home advantage of covariate. So once we've done that, that's all that we need to now bring in this additional factor. So you can run those changes and have a look at the results, and how would you interpret what it indicates about the home field advantage. So what does that suggest? So we find if we look at the summary and we go to our covariate, we see a negative value. So remember that we're looking here at the factors that relate to the chances of the home team winning, and this is suggesting that it's reducing the chances by playing at home, which goes against conventional thinking. Generally, it's believed that the team or players that are playing at home have an advantage by playing at home. There's many theories of why this happens, but that's the general result. So it seems like something is wrong, potentially wrong here in how we've specified our model. We can also look at how the abilities change, but just for the sake of time, I'm going to focus on what could be going on with this reverse home advantage. So what might be a problem here that could lead to this kind of surprising result? Yeah, so because of the way that we've handled draws, we've kind of created a link between the home team and the draws, and it's one that's disadvantageous for the home team because we're assigning losses whenever there's a tie by the way that we specified the outcome. So that could be the first thing that we would think of when we see this kind of peculiar result. So to try to see how much this could influence, let's maybe first look at how many ties are we actually dealing with. Because if it's very few, you'd be surprised that it could have such an influence on the results. So how common are ties in this particular season of the EPL? Well, to look at that, we just need to look when there were actually draws. And so I've just defined this ties variable. And then I can just summarize that in a plot, or simply just take a table. But this is what you'll see. So the left are the count in the season of matches that did not end in a draw. And on the right are the instances where they did. And we can see that there were about 100 cases. So it's about a quarter of the total result. So definitely not a negligible proportion. So this tells us, okay, maybe we do need to deal with this. So to see how it might actually be influencing, we can look at the subset of results that did not involve draws. And that at least will give us some idea if that looks very different from what we see in the full data set, that would suggest that the way that we're handling ties could be problematic and that our results are sensitive to that. So the way that you could do this would just be to filter out those draw cases and then just refit the model as we did before. So here I've just gone through those steps and isolated the at-home factor that resulted once we excluded ties. And what do we see happens? Our estimate, it's now significantly positive. Okay, so there's been a sign change, and one that's a significant change. So that reversal by excluding ties does lead us to conclude that the way that we're handling ties is not adequate, and that we need a better method to deal with that. Now, unfortunately, with the standard Bradley-Terry, it doesn't actually handle ties itself, but there is work that's been done, and actually one of the package authors has recently given a paper that provides a method for tie handling. For simplicity, I mean, you could imagine approaches like randomly assigning a win or a loss to just eliminate that connection between the home team and ties. That could be one strategy. But ideally, you would like to model draw outcomes directly, and there are approaches to do that. But unfortunately, the particular implementation of Bradley-Terry 2 doesn't have them. But in any case, I hope that this introduces you to the basic idea of paired comparisons. And there are many forms of these models. Actually, if you've heard of the ELO system, that's another special kind of paired comparison model. So getting familiar with these is really important if you're interested in rating systems. And again, there are applications of this that would go beyond sports data. You could imagine, for example, using a paired comparison model to put scientific journals head-to-head based on their citations or things like this. So it's a useful set of models to be familiar with, and they definitely have a valuable applications in sport. Okay, so I'll take a break at this stage, and we can reconvene at 3:30, and if any of you have questions, I'll be here during the break. Yeah, so you're free to go, and then please come back at 3:30 so we can wrap up the rest of the modeling section.